Okay. So we're happy to have Tony Pantev from Philadelphia, and he'll speak about symplectic structures on moduli of Stokes data.
Thank you, thank you. So my slides are visible, right?
Yes.
Okay. Well, so I want to first start by apologizing to those of you who have heard some versions of this talk. I tried to give one of these last year in the Higher School of Economics. It was kind of garbled. So hopefully this one will be slightly better. Yeah, so let me just say what this is about. First of all, it's a joint work with Dima Rinkinen and Bertrand Toen. And it's really about a general framework that we wanted to develop that will allow one to understand symplectic structures in the relative situations. So we want to look at families of derived stacks or sheaves of derived stacks over a topological space. And we want to understand what would it mean to have a symplectic structure specified along the fibers and how to construct those. And then once the framework is in place, the application we want to pursue and the application that was the main driving force behind the project is to understand the moduli of Stokes filtered local systems on a smooth variety over the complex numbers, construct the Poisson structures on those that will be shifted in higher dimension, and describe the symplectic leaves of those Poisson structures. So this is the plan, and now let me plunge into the story. So let me recall somehow the basic setup of meromorphic connections in dimension 1, just so that we understand what the objects are that we are studying, what the moduli spaces are. So say that we have a small disk D in the complex plane centered at 0 and the corresponding puncture disk. Now a meromorphic connection on the disk with poles at 0 will be just a homomorphic bundle on the puncture disk and a homomorphic connection on that bundle on the puncture disk, but we'll put the condition that it satisfies the Leibniz rule for multiplication by meromorphic functions on the whole disk. So that's the same as saying that the bundle extends to a homomorphic bundle on the whole disk, and the connection differentiates and gives you only finite order poles. And it doesn't matter which extension you take. And so the standard terminology that I'll be using is we're going to say that the connection has a regular singularity or a tame ramification at 0 if we can find a homomorphic extension to the whole disk so that the connection has a logarithmic pole, first order pole. And otherwise, we'll say that it has an irregular singularity or a wild ramification at 0. And let me just recall the most basic version of the Riemann-Hilbert correspondence, which is relevant to this picture. So if you take a meromorphic connection on the disk and a circle centered at 0 inside the disk, then the nabla horizontal analytic sections of our bundle on the puncture disk will give you a locally constant sheaf on the puncture disk, which you can restrict to the circle. You'll get a locally constant sheaf of vector spaces on the circle.
Excuse me.
Yeah.
Hi, Tony. May I ask you? You said regular connections. How did you say in the previous slide? Regular singularity.
Yeah.
It's not quite this, right? There is some regularity. Is it about this? I mean, there is some growth in sectors.
No. Regular singularity. There are no sectors. So regular singularity is just a logarithmic connection. The sectors are for the irregular ones. I'll come to the sectors in a moment. So regular singularity is just a logarithmic connection.
Okay.
Okay. Yeah, I mean, that's why I wanted to put down the terminology so that, you know, we all understand what I mean. So, yeah, so you know, you have the Betty version of the connection, which is the horizontal, number horizontal analytic sections on the circle. And the really basic version of the classical Riemann-Hilbert correspondence says just that this assignment gives you an equivalence of categories between the tamely ramified meromorphic connections on the disk and the complex local systems on the circle. And now in the irregular case, this is way too naive and it doesn't work. So what you need to do when you have a wild ramification, when you cannot choose a homomorphic extension, a lattice where you have a logarithmic pole, what you have to do, you need to put extra data on that local system on the circle if you want to reconstruct the connection. So if you're looking for the Betty incarnation of the RAM data, the connection, you need extra data on this local system on the circle. And so this is the Stokes structures, whose moduli we're going to study. So we're going to really study the moduli of these Stokes structures. There are many ways to codify Stokes structures. I mean, classically, you do it by Stokes matrices. So you break the disk into sectors where the analytic sections of your connection are convergent with temperate growth. And going from one sector to another, you need to make a change of frame, which is given by a matrix. So you have this collection of Stokes matrices, which captures the right data. The problem is that's kind of unwieldy to work with because there are a lot of equivalences that you need to specify on those matrices. And those are not easy to list. So they belong to certain unipotent groups, which change locally from ray to ray in the breaking into sectors. So it's kind of unwieldy to work with them. So a better picture, which is the one we're going to work with, is due to Deligne and Malgrange. And rather than doing matrices and choosing special frames, you use filtrations. So there is a formalism for encoding Stokes data, Stokes structures of Deligne and Malgrange, which puts a filtration on this local system S on the circle. So let me quickly review that. So if you have a meromorphic connection on the disk, then this connection actually defines for you a finite cover of the disk. In fact, what it defines for you, it defines a constructible sheaf of finite partially ordered sets on the disk. So I'm calling that sheaf Deligne sub and nabla. I mean, we'll upgrade that a little bit later on when we study the symplectic problem, but for now, I'm just going to call it that. So as a sheaf of sets, if you ignore the orders of the Stokes, it is a local system. So it's just a finite cover of the circle. So it's a bunch of circles, each of them wrapping the basic circle some number of times.
Sorry, is that the locally constant sheaf of solutions, or is something else?
No. This is what's going to label. This is what's going to label the steps in the filtrations of the Stokes filtrations. So if you want to think about these things explicitly, so I didn't create slides about that, but if you want to think about these guys explicitly, is what you really need to do is you need to look at solutions, convergent solutions on sectors. And you need to look at the growth of the eigenvalues for those solutions for the corresponding system of ordinary differential equations. So they're ordered. There are finitely many eigenvalues corresponding to maybe groups of Jordan blocks, which are ordered by growth in the sector. And so this is the set that this Deligne and nabla parameterizes. So it's just a finite set, and it's ordered. It's a finite set that varies with the points on the circle. It's ordered for each point, partially ordered. but as a set, it's really locally constant on the circle. It could have monodromy, but it's locally constant. And this guy, if you include the orders, it's a constructible sheaf with respect to a stratification on the circle. And the stratification is very simple. You just braid the circle into a bunch of arcs with points. So those points, which I've denoted here by 5e, they're called the Stokes rays. In fact, in the classical terminology, they're called the anti-Stokes rays, but you know, it's a mouthful to say anti-Stokes rays, and the Stokes rays are never going to appear, so I'm not going to call them Stokes rays. So there are finitely many arcs which meet at points. The circle is just broken by a bunch of points. What's happening it's that on each arc, we have a constant sheaf of sets, which is actually a constant sheaf of totally ordered sets. So the order is not even partial on the arc, it's total. And when two arcs meet at a point, the order at that point is just the minimal of the two orders incoming to that point. So that's a property of this Deligne sheaf that's associated with every meromorphic connection. And then another data that you get now on the solutions, as you were asking, on the flat sections.
Tony,
yeah.
Do I understand correctly that like the simplest example is that at this special point there are two points which are uncomparable and they become ordered in one direction when you move to one arc, right, and oppositely ordered
that's
in
right.
the other arc, that's right? Mm-hmm.
Yeah, let me finish. Maybe that you know the behavior of solutions will tell you will give you a little bit more of a picture. So if you have that sheaf that labels the steps of the Stokes filtration, it actually doesn't depend on the connection itself. It depends on its irregular type, which is the gauge equivalence class of the connection. In fact, not of the connection, but just of its Laurent tail, up to meromorphic, convergent meromorphic gauge transformations. So connections that are gauge equivalent give you the same sheaf like that. And once you have the connection, then if you look at the local system of solutions, it's equipped with a local filtration by subsheaves, where the filtration is labeled by this constructible sheaf of posets. And on each arc, the filtration is constant with non-trivial factors. So, you know, there is no dummy degeneracy in the filtration. And at each Stokes ray, at each point where the two arcs meet, if you take the subquotient, a subquotient for the order for the filtration on that point, now you on that subquotient you get two filtrations, one coming from the left, the other coming to the right, from the right. And again, a property of this picture is that these two filtrations are opposed in the Hodge theoretic sense, in the linear algebra sense. So that's exactly what Sasha was saying, that there are two of them, but you cannot quite order them. Once you cross the ray, they change order. And so that's the picture. Every meromorphic connection on the circle gives you this labeling set, this constructible sheaf of labels, and it gives you a filtration on the local system of solutions. And that's the Beatty data that you should associate with the connection. So if the connection is logarithmic, all this extra data is trivial. It's not there. But if the connection is if the connection is not logarithmic, then it's there. Yeah, there was a question?
Yeah, so I mean, Sasha described the simple case, but there could be more complicated reordering.
Yeah, there can be more complicated. And I mean, the actual transition is this oppositeness condition, right? I mean, the oppositeness doesn't just mean that.
Is it obvious that oppositeness is well defined in whatever reordering? I mean,
well, it's not always reordering, right? I mean, it's just oppositeness of two filtrations on the same vector space. I mean, you can. I mean, sometimes, you know, if only two steps in the filtration exchange place, then it will be reordering. But in general, it's not, which is supposedness.
What does it mean exactly? What does it mean formally?
Formally just means supposedness. You have two post-filtrations on the same vector space. It means that if you pass to the double associated graded, it gives you a decomposition.
In what degrees? I mean, there should be some correspondence between the indices, right? I mean, just say.
No, they have the same length. The two filtrations have the same length. So
length number. Okay, yeah, all right.
Yeah,
okay.
There is no question about the degree.
Okay.
Excuse me, why did
that was that statement about, that's part of the statement about saying that the labeling set gives you a local system of sets, actually. Because the labeling set, if you ignore the order, if you just look at the set, it just gives you the associated graded with with respect to the filtration.
So it doesn't change. Yeah.
Excuse me, Tony, is it a sheaf of sets, not of vector spaces, right?
It's a sheaf of sets, yeah.
Why did you say about linear algebra?
With, you know,
yeah, I understand, right? Yeah. But why did you say about some vector spaces, some linear algebra?
No. The sheaf of sets,
okay,
is the thing that labels the filtrations on the local system of vector spaces. You know, the
okay, I understand, right?
Yeah. And you need this extra data on the local system of vector spaces. So these are like the moderate growth sections in sectors. These are these guys. Yeah, sorry, I didn't prepare a slide with that. I mean, you can actually write that very explicitly, but if you, I mean, it is in the Lin's letter to Magrange, and it's also in the paper that we wrote with Maxime and Ludmil on Koch theoretic aspects of mirror symmetry. So you can see the formulas there. Anyway, so let me wrap this up. So this filtration labeled by this constructible sheaf is the Deligne-Malgrange-Stokes filtration, and it is called the Stokes structure associated with M nabla. And the irregular Riemann-Hilbert correspondence in this setting is saying that the functor that associates to a connection this filtered local system, but filtered by steps that are labeled by a constructible sheaf, which depends on the connection, it's an equivalence of categories.
So in particular, the Deligne filtered sheaves is a tensor category, yeah?
Say it again?
So in particular, the Deligne filtered sheaves form a tensor.
Tony, you switched off your mic.
Sorry, it was my mistake.
Okay, it should be okay now.
Now it's okay.
Yeah, sorry. What I was saying is that it is a tensor category. It's not obvious that it is from the definition, because my labeling constructible sheaves depend on the connection. But in fact, the way Deligne and Malgrange do it is they're all subsheaves in some local system, complex local system, which has partial ordering. And from that, it's actually very easy to see that it's a tensor category already in the Betti setting.
So if you take tensor product of two objects like that, then what do we do with the Deligne sheaves? We just take their product or something more sophisticated?
No, the Deligne sheaf of their product, it's some kind of a convolution, right? Because you're taking the direct eigenvalues for the connection on the tensor product.
So do Deligne sheaves form a category themselves?
They do as subsheaves. So, you know, you can ask.
What are the morphisms in this category?
Yeah, there are morphisms. So there is, as I said, there is a complex local system, which we can call Deligne, that doesn't depend on anything. It's a complex local system on the circle. And it, you know, corresponds to all possible growths on sectors for forms with Puiseux coefficients. And the Stokes are ordered. And the Deligne sheaves are subsheaves in that local system with induced order, which are finite. And the natural morphisms between them are inclusions. Or you can ask for morphisms which are induced by linear maps on that complex local systems. That's actually what gives you what you need for the tensor structure.
But the points on the circle, are they canonical somehow? Because you can probably
no. The points. in this local system, the points, they're all possible sectors and all possible points. For a fixed meromorphic connection, the points are canonical, right? They are the ones where canonical in the sense that, of course, there are automorphisms of the picture. You can move them around in the circle when you choose your sectors, but the types of sectors always stay the same. The question was about the morphisms between these Lin sheaves, so there are natural morphisms as subsheaves. So there is actually a real subtlety here, which I swept under the carpet, which is that each irregular type or each meromorphic connection gives you one of these Lin sheaves, a subsheaf in that sheaf of forms, the Puiseux forms. The problem is that not every finite subsheaf that satisfies these properties, the properties that I listed, these properties. Not every finite subsheaf in the sheaf of Puiseux forms that satisfies these properties is coming from a meromorphic connection, and that's actually very strange because you would expect that anything that looks like that will really be you'll be able to regenerate it to an actual connection. But unfortunately, it's not. And the example is kind of subtle. So for a long time, I thought that everyone should come, but I didn't have a proof. So there is another interpretation of these sheaves. They are front projections of Legendrian knots in the sphere. And so everyone comes as a front projection of Legendrian knots. But not everyone comes from a meromorphic local system on the circle. And so there is an example that Maxime told me about, which is due to Giroux, of a front projection of Legendrian knot that gives you one of these sheaves that does not come from a meromorphic connection. But it's kind of subtle. I've actually never digested it. And it was found fairly recently, maybe 7-8 years ago. So there are these sheaves that you can define abstractly. There are maps between them, but somehow the category of those sheaves, the subcategory of those sheaves that comes from local systems is kind of smaller than what you define abstractly, and it's not quite clear how do you recognize it in the natural category that you define. Yeah, sorry, question?
So it's not known the image of the functor.
The essential image of that functor, well, there is no intrinsic description for it. Yeah.
I see.
But doesn't this contradict to the functor being in equivalence?
No. This, the functor is not just the Lin sheaf, it's the Lin sheaf plus the Stokes filtration on the local system.
Do you mean that there are some Lin sheaves on which you cannot put a Stokes system?
Yeah, exactly. There are some Lin sheaves that do not have an accompanying Stokes filtered local system. The Lin sheaf is just the thing that labels the steps of the filtration, and there are some Lin sheaves that you cannot lift to a filtration. But once you lift it to a filtration, then it, of course, it
I guess the answer is that it's equivalence with the image of the functor, right? The answer to
no, there is no statement about the functor. The functor really has two pieces in the way I've described it, right? It has a piece which is giving you this labeling guy plus the Stokes filtration on the solution local system. There is no statement that says that only the labeling guy reconstructs. The statement is that the Stokes filtered local system reconstructs with its own labels. In fact, that's what I said. The way Lin and Malgrange do it, they don't specify the Lin sheaf. They just say, look at all possible omegas and look at all possible steps. Some of the steps are actually trivial, but then you don't need to do anything. And then the Stokes filtered local system reconstructs.
And you also mentioned Legendrian knots, right?
Mm-hmm.
Are they related to meromorphic connections?
The node by itself is not, but there is some indirect relation between the Legendrian node that appears here that labels the Stokes data and meromorphic connections. It's kind of indirect. It uses the non-abelian Hodge correspondence. This moduli of Stokes data, there is a non-abelian Hodge moduli that's isomorphic to it that consists of irregular Higgs bundles with certain Casimirs and certain data at infinity fixed. And the irregular Higgs bundles, they all have spectral curves. And those spectral curves are actually singular at infinity. And the link of that singularity is the Legendrian node. But that's actually it's in some cases it's proven. It's a theorem of Schende, Truman, and Zaslow. But no, it's not proven in general. That's like experimental evidence. There is no direct relation between the connection and the Legendrian node. They just describe the same type of discrete data.
Why is it a node? So it lies in the cotangent bundle or something?
Well, it's a link. It's not really a node. It's a link. It's
right.
Yeah, it lies in the cotangent bundle.
Cotangent bundle, so it's a sphere. Okay. Thank you.
Okay, can we move on?
Yeah.
Are we happy? Okay. Okay, so here's the motivating problem. If you take a smooth projective curve, puncture it at a finite number of points, and specify Laurent tails for connections at each point.
Switch the slide because we didn't see it.
I switched the slide, yeah.
We're still on the same one.
It doesn't say motivating problem?
No, it's still the same dilemma Malgrange.
Huh, weird. For me, it's different. I don't know.
Maybe you can stop sharing, then resume or something like that.
Yeah, I'll try. Yeah, hold on a second.
Maybe when Kostya switched off your microphone, you also switched off your sharing or something like this.
Well, how about now?
Now it's fine. Yes.
Okay. All right. So here is what the object we want to study is. You fix this fracture X, which is a smooth projective curve, puncture it at a finite number of points, and at each point we specify a Laurent tail for a connection of rank R. So it's a Laurent polynomial with coefficients in the Lie algebra, in GLR here. And then we look at, so each of those Laurent tails, each of those irregular types gives you a Deligne sheaf, one of the sheaf of posets, constructible sheaf of posets, on a circle around the puncture. And we look at the moduli stack of Stokes filtered local systems where at the punctures, the Stokes filtrations are labeled by Deligne sheaves, by those Deligne sheaves. So that's the moduli problem you want to study. And the goal is to construct a Poisson structure on this guy, describe the symplectic leaves of that Poisson structure, describe that Poisson structure in the usual way you describe Poisson structures on character varieties. So, this is like the Beatty data of connections. So it's like a character variety with irregular singularities. And you want to describe the Poisson structure or the symplectic structure either by deformation theory, by some cup product on cohomology, or by reduction picture, like Hamiltonian or quasi-Hamiltonian reduction. And you want to extend this whole story to other structure groups and to higher dimensional varieties. And so this framework that we developed, it does all of this for you. let me just say that, of course, the Poisson structure and the symplectic leaves, it was known before due to work of Boauch and Yamakawa. But it was known on the smooth locus of the moduli of local systems. And in some sense, that's a very good answer already, because if you choose your irregular type generically, so there is a stability condition that you can put on the irregular type. If you choose your irregular type generically, and the data that specifies the symplectic leaf is the formal monodromy at infinity, if you choose that one generically, if you choose them to be stable, then that stack is actually a smooth scheme. And so the answer of Boauch and Yamakawa actually is complete. It gives you the Poisson structure and the symplectic leaves. What our point of view adds to the story, it tells you what happens when you're not generic and when you're not smooth. So it works at all points. And another thing we do that wasn't known before is we actually have a topological, cohomological description of the symplectic structure and the Poisson structures. So Boauch and Yamakawa, they only did the quasi-Hamiltonian description. And the cohomological description wasn't quite clear. The cohomological description is completely clear when you don't have ramification or where you have tame ramification. So when you don't have ramification, it boils down to Poincaré duality with local system coefficients. And when you have tame ramification, it boils down to Lefschetz duality with local system coefficients. And in this setting, it wasn't known. And of course, you know, you'll see, I mean, there is only one thing it can go down to. It boils down to Verdier duality.
How is it different from the cohomological description, which you can get if you use the Durand picture? In the Durand picture, I think it's easy to write some kind of cohomological description.
That's right. No, I mean, it should be the same, but then you really need to do the analytic Riemann-Hilbert correspondence carefully in order to say that the two pictures are the same. So it's true, yeah. In the Durand picture, you have a cohomological description, and you know, a priori, the analytic part of the Riemann-Hilbert correspondence, you know, the statement that the Durand moduli stack with irregular singularities and the Betti moduli stack with irregular singularities are analytically isomorphic. Well, it's not quite done. I mean, for curves, it's actually done, but in high dimensions, it's not quite done yet because of the derived structures. You know, in order to put the symplectic structures and the Poisson structures there, you need to do this in the derived stack world. Even in the stackiness is a problem. So there is some work to be done there, but actually there is a recent work of Porta and Tessier who actually do it carefully. And they also prove the representability of the Durand stack. Sorry, of the Durand stack was done by Tessier before, of the Betti stack, which wasn't known. And in fact, yeah, it's kind of strange because here, when we construct the symplectic or Poisson structures, we need very mild representability. We don't really need to know that those guys are algebraic. So you can prove it for the moduli of Stokes data without knowing representability, but they are actually algebraic. So that's known, and then there is an analytic isomorphism. You still need to prove a comparison theorem, Sasha. I don't know. You know, we haven't looked at that, but it should be there.
Okay, thank you.
Okay. So here is, so I'm switching gears now. I'm going to talk about constructing these relative symplectic structures and understanding them first and then constructing them in some explicit way. So the problem is to start with a sheaf of derived stacks over a topological space S. I'm calling the sheaf F. And you want to describe the notion of a symplectic structure along the Stokes. And so coming back to the representability, in order for this to work, I mean, to make sense, you need to put some representability conditions on the Stokes of that sheaf. For instance, they should be algebraic stacks. That's more than enough. Much less is sufficient. I mean, you know, like formal local representability is enough. And that's all we need and all we use, which this is very easy to check for these stacks of Stokes filtered local systems or for the stacks of connections. But you need a little bit of representability, because at least you need to be able to talk about tangent complexes. And then you need to somehow come to grips with the non-degeneracy condition on the forms. So once you have enough of a structure to be able to talk about tangent complexes, you can talk about forms. But then you should be able to talk about the form being non-degenerate on the family. So that requires some notion of duality on the base, because you look at sections of your family, and so you'll pull back the tangent complexes. This will be complexes of vector spaces on the base, and you need to be able to say what it means for such guys to be dual. So you need some notion of duality in the shift theory on the base. And as I said, the natural notion and the one that really works here is the Verdier duality. And in fact, you can build the whole theory, which is what I'm not going to do, for locally compact Hausdorff spaces S, and use the covariant Verdier duality of Lurie that identifies shifts and co-shifts, and say what the non-degeneracy of symplectic form is. And the whole theory works. Even the push-forward theorem, which is the main tool, works. The problem is that it's not useful for computations. So when you really want to compute things, you want to have type of a duality that's computable. And so you want a version of Verdier duality that's computable. And so that's why, rather than looking at arbitrary topological spaces and arbitrary shifts of stacks, we're going to look at stratified spaces and constructible shifts of stacks, where we can use just the usual Verdier duality for the induced shifts of complexes of vector spaces. Okay, so let me quickly talk about these shifted closed forms and symplectic structures. So I don't have time to go into that in depth, but I've given many talks that you heard me talk about these things, and hopefully you've seen it, so I can go quickly over that. So this is something we did 7-8 years ago with Bertrand and Michel and Gabriele. So if you have a derived Artin stack, which is nice, smooth, so that means locally finite presentation over a base field, then you can define a complex of closed forms of that stack. And being closed in this case is extra structured because of the internal differential in the cotangent complex. So being closed is a co-cycle condition in the double complex for that internal differential. So if the stack corresponds to a DG algebra, commutative DG algebra A, then this complex of closed P forms, it's just modeled on the stupid truncation of the de Rham complex. So it's the total complex of the P step of the algebraic de Rham complex, but total with respect to the product. So you need to complete because you can have because of the graded commutativity, you can have forms in arbitrary. I mean, you can have elements in the forms in arbitrary degrees because you have symmetric products. So you really need to complete.
These are forms, are they?
Say it again?
These are holomorphic forms, right? Not C infinity or anything.
No, these are algebraic forms, yeah. Just scalar differential.
Why not omega then? Why A is different? I mean, usually they do not formed by omega, right?
Yeah, I mean, I don't know. That's the notation we chose originally, and I mean, because when you do it on schemes, you're really taking the stupid total complex of the stupid truncation of the algebraic de Rham complex, and so it doesn't quite look like the forms. It looks like some sums of forms. So we call them A.
Yeah. Tony, do you mean FP of A or FP of de Rham of A? In the second,
yeah, FP of A is FP of de Rham of A. I mean, just a shortcut notation. And so an n cocycle in the complex of two forms, closed two forms, is what we call an n-shifted two form. And it's an n-shifted symplectic structure if when you look at its basic term, it's internal homological degree zero term, and you contract with it the tangent complex, you get the cotangent complex shifted by n. In this quasi-isomorphism. So that's the non-degeneracy condition. You can also talk about isotropic and Lagrangian structures. So if you have a map of derived stacks, an isotropic structure on such a map is a shifted symplectic structure on the target, and then a co-boundary between the pullback of that symplectic structure and zero, or homotopy between the pullback and zero. So a co-boundary that bounds that cocycle. And the isotropic structure is Lagrangian in the usual way if it satisfies a non-degeneracy condition, which means that when you contract with it, the relative tangent complex of the map becomes identified with the shifted cotangent complex of the source. So that's like the usual statement that something is Lagrangian if its normal bundle is isomorphic to its cotangent bundle by the contraction with the symplectic form. And there is a little bit of chicken and egg here situation because you can actually set up the whole theory with Lagrangian structures, or you can set up the whole theory with symplectic structures. And one of them is reconstructed from the other. So for instance, if you take a stack and you look at the structure map to the point has only one symplectic structure, the symplectic structure 0, which you can put in any homological degree. And if you look at the Lagrangian map, if you look at the Lagrangian structure on that map, that's the same as a shifted symplectic structure on the source with a shift one less. So there is a whole slight ambiguity on how you want to build your theory, but it's actually convenient to talk about both of them at the same time, and just remember that one of the notions actually does reconstruct the other.
Sorry, did you say it should be n-1 shifted?
Right. So if you choose the 0 symplectic form on the point with shift n+1, then the Lagrangian structure will be an n-shifted Lagrangian structure.
Do you mean it's inconsistent in this phrase?
No, it is, because my definition of an n-shifted Lagrangian structure is an n+1 shifted symplectic structure plus. Yeah. It's just a labeling issue. Yeah.
This finite presentation, what does it imply for the cotangent complex? Is it perfect?
Perfect. Yeah. So that's the thing that I mean, there are things that are not the finite presentations which occasionally have perfect tangent complexes, but if you geometrically want to recognize situations where the stack behaves like a smooth guy, the finite presentation is the correct thing.
So all sorts of duality, there is no issue. I mean, perfect.
Yeah, exactly. Yeah, that's why you want to have the perfect tangent complexes. And just a remark, if you haven't seen this before, it's something to keep in mind, which is that, when you have these derived stacks, they have stackiness and they have this extra nilpotence, homological nilpotence in their function theory. The function theory is a DJ algebra. And the tangent complex or the cotangent complex, it recognizes these additional structures by pieces in different degrees. So the stackiness is reflected in the positive degrees of the cotangent complex, and the derived structure is reflected in the negative degrees in the cotangent complex. And the symplectic structures actually identify those. So it's really essential to have these extra structures if you want to have a symplectic structure. And also, of course, it's essential to have them to resolve the singularities, to have a perfect guy. But yeah, I mean, it's something that's somehow built into the geometry.
Excuse me, is it finite degrees in both directions?
Yeah, it's a perfect complex. I mean, they are, you know, for things that are not locally finite presentation, there is a notion of almost locally finite presentation, which is due to Geisgori and Rosenblum, which is essentially as good for this theory as the locally finite presentation, and you get many more examples where your complexes are not necessarily perfect, but they're kind of perfect. So there's still a finite homological amplitude, but the Stokes could be vector bundles of infinite rank. I mean, the Stokes the terms could be vector bundles of infinite rank, and somehow the theory works because there is a completion there. And but I'm not going to talk about this situation. I'm just going to assume local finite presentation. Okay, so just a couple of easy examples of these forms and symplectic structures. If you have a reductive group, then choice of a non-degenerate invariant form, quadratic form, gives you a two-shifted symplectic form on the classifying stack. Because the cotangent complex of the classifying stack is just the Lie algebra, the dual of the Lie algebra in homological degree 1, and the second wedge of that shifted by 2 is just just the quadratic forms. And you know, if you want it to be on the stack, they have to be G invariant. So killing forms are symplectic forms on classifying stacks. They're closed. I mean, the closing data here, it's actually contractible, so there is no extra piece of information. And another very easy example is a shifted cotangent bundle. So you take a cotangent bundle and you put the fiber in homological degree n. And so that gives you either a stack or a derived space, depending on whether the shift is positive or negative. And this, the usual standard symplectic form of the cotangent bundle, becomes a shifted symplectic form of that stack or a derived space. Okay, so now I'm going to talk about a very general notion of quasi-Hamiltonian reduction that allows you to produce these shifted symplectic forms on spaces. And in particular, it allows you to talk about relative ones that are specified on the Stokes of a constructible sheaf of stacks over a stratified space. So first, I'm going to talk about it diagrammatically. So we'll start with the index category, which, you know, the most general thing you can take is a finitely presentable infinity category, but you can just take a pole set, which is going to suffice for all the examples, and take a category of values which has finite limits. And now F dot will be a diagram of shape I in C, so just a functor from I to C. And, you know, so I'm going to list it, list all the values of the functor as F alpha for the alphas in I in my indexing category. So you have a global sections of such a diagram, just the limit of these objects, because we're assuming we have a finite limits. And in order to talk about forms, we'll need some covariant contravariant story. So what you really need is the category of twisted arrows in I. So this is just the standard homological tool. You look at the category, which essentially looks like the category of morphisms in I, but so the objects are morphisms in I, but the maps between them are not morphisms of maps, but are commutative diagrams in which the map on the source is reversed in direction. So these are the twisted arrows, and they're composed in an obvious way. And so the category of twisted arrows has a natural functor to its source. Each twisted arrow you can map to its source or target. So you get a functor to I and the opposite of I. And now you can use that to talk about forms on diagrams of stacks. So suppose that you have a diagram of Stokes, derived Stokes labeled by I, I'm calling it F, and I'm gonna add an extra layer of flexibility by allowing my forms to have coefficients in complexes of vector spaces. So I'm gonna have a diagram of complexes of vector spaces labeled by I again, I'm calling it E. And then you get a functor labeled by the twisted arrows in I of complexes of vector spaces, where you send an arrow to the forms on the stack corresponding to the source, tensored with the complex of vector spaces corresponding to the target. And complex of closed P forms on the diagram of Stokes with values in the diagram of vector spaces is just the limit of this guy where the indexing set are the twisted arrows. So that's solving this problem of the forms behaving well under pullbacks and the coefficients behaving well for push forwards. And this space of forms on the diagram with values in E is defined as the cohomology of this complex, or it's slightly better to think about it as a space. So you take the dot can associated to the non-positive truncation of the complex and take its topological realization. And so an E-valued form, P form on F is just a path in that space. So it's a degree 0 co-cycle in the total complex. And a good thing to remember is that you actually have, for these diagrams of Stokes, you have for the corresponding diagram complex of forms, you have a global section map, which gives you an element in the closed P forms on the limiting stack from the diagram with coefficients in the limiting vector space for the diagram again. Now I'm going to use that to define relative forms and say what it means for them to be non-degenerate. But I need to talk a little bit about co-specializations to say it properly. By the way, so how am I doing in time? How much more time can I take?
There is no rush. Like
no
1 hour.
rush. Okay. Okay, great. So at least I can probably get to something. Okay. So let me just recall the standard Recall-Mann story. So if you have a nice topological space, say a CW complex, and you have and you break it into a closed and an open. So you have a closed subspace and a complementary open, and you have a value category with small limits and co-limits. And if you have a sheaf on X with values in C, then you can reconstruct that sheaf from its restriction to the closed and its restriction to the open by giving yourself one piece of gluing data, and that's the co-specialization map. It's a map of sheaves on the closed, and it's the map that goes, it's just the unit of the junction from the pullback to the push forward for the open immersion. And it is the map that goes from the restriction of the sheaf to the closed to the pullback of the push forward of the restriction of the sheaf to the open. And so this assignment that sends a sheaf to its restriction to the open, restriction to the closed, and the co-specialization, it actually gives you some homotopical equivalence of the category of sheaves and the lax op limit of this gluing factor from the sheaves on the open to the sheaves on the closed. And the key observation is that you can apply this to strata in a stratification. And if you use this co-specialization gluings for the strata in a stratification, you get a combinatorial picture for closed forms and symplectic structures on a constructible sheaf of stacks. So let me try to explain this. So start with a good stratified space. By the way, I didn't say that, but when you look at the slides later, there are these yellow things. They are actually explanations. So if you click on this, you'll get to some explanation of what good means, but I don't want to go into this now. So there are many of them here and there where I said something without actually explaining it, but then there is a link in the slides to some explanation at the end. Okay, so start with a good stratified space. So for those of you who know, it means that the stratification is conical and finite. Take a finite poset that labels the strata. So X alpha will be the stratum corresponding to the label alpha. And let's look at the constructible sheaves for this stratification of spaces. So F alpha will be the restriction of such a sheaf to the stratum X alpha. Now, about the co-specialization gluing, if you have a stratum and you have any closed set that contains that stratum as open, and you take the complement of that closed set, then you get a sheaf of nearby cycles on the stratum, which is just restrict to the open, push forward, and then pull back to the stratum, to the closed and restrict to the stratum. And then you have a co-specialization map. And the point is that this actually does not depend on the closed set. Any closed set, for instance, the closure of the stratum will work. Any closed set gives you the same nearby cycles and the same co-specialization. So this is not really the co-specialization for the stratum. It's like integrated over all closures, all closed subsets containing the stratum as an open. So they depend only on the stratum. They don't depend on the closed set. And this sheaf of nearby cycles and the co-specialization, the collection of all those. So you have the sheaf, the constructible sheaf, its restriction to its stratum, its nearby cycles on the stratum, and then you have a co-specialization gluing between the two. So this data, it's some combinatorial machinery that actually reconstructs the sheaf F. And it works not just for sheaves of spaces, but with sheaves with values in interesting geometric categories, infinity categories. And that's what we are gonna exploit. So it makes sense for any category, sheaves with values in any category that admits finite limits. So for this, you just need to take the correct combinatorial picture, and the correct combinatorial picture is your diagrams are going to be labeled by the category of exit paths for the stratification. So these are homotopy classes of paths that have one end anchored at the stratum, and then there is an infinity category structure on that, which is very explicit, simply show. So if I is nice, if I say a finite poset or a finitely presentable infinity category, then this exit path category is also finitely presentable. And the constructible sheaves for the given stratification are just the diagrams of simplicial sets labeled by this exit path category. And so for any category with finite limits, you can define the constructible sheaves with values in that category as the functors, as the diagrams in that category labeled by the exit path category. So these are the C-valued constructible sheaves on X for the given stratification. And now for such a guy, for such a sheaf, you actually get all the whole package of standard objects in function theory, in sheaf theory. So if you have a point in X, it gives you a label. It gives you an element in the exit path category. This is just all the paths emanating from that point. The value of the functor on that is the stock at the point. You have global sections, which is just the limit of the diagram. We have an evaluation map from the global sections to the stock for every point. If you have a stratum, the fundamental groupoid of that stratum, it's actually a full subcategory in the exit path category. it's just the subcategory spanned by the paths emanating from that stratum. And the value of the functor or the diagram on X on the stratum is just the restriction of that functor on that subcategory of paths, which really is the fundamental groupoid. So this is a local system on the stratum. Yeah.
Yeah. Final groupoid in some kind of infinity sense, right? So you also take.
Yeah, everything is in the infinity sense. Yeah, everything is in the infinity sense. Yeah. And so if you fix a stratum, then you have these paths that land in the subcategory of, so it's this comma category of paths that land in the subcategory of paths emanating from the stratum. And then you have the third subcategory consisting of all guys that are not weak equivalences. And then you can define the nearby cycles for your sheaf with values, constructible sheaf with values in a category to be the right can extension for the restricted functor along this functor from the guys that are not an isomorphism to the guys emanating from the stratum. And you have a co-specialization map by the universal property of the right can extension. It goes from the local system, the restriction of our constructible sheaf on the stratum, to the nearby cycles. So if you have one of these constructible sheaves, which is really a diagram on the exit path category, you get immediately the full package. You get the local systems on the strata, and for each stratum you get nearby cycles, and you get the co-specialization map. And
so in this situation, we have a disk and a point. This recovers the usual nearby cycles.
Yeah. It recovers the usual nearby cycles for
not
strips of
just
spaces,
yeah,
or complexes of vector spaces, or anything that's stable.
okay.
Yeah. So now if you have a nice stratified space and strata labeled by finite poset, now choose a sheaf of constructible sheaf of vector spaces and a constructible sheaf of stacks. So it's these diagrams. Then you can define the space of a complex of closed p-forms with values along the fibers along the stocks of the sheaf with values in E. And you can define global closed evaluate p-forms. And you have a global section map, which goes from the global forms to the closed p-forms on the global section of the sheaf of stacks, tensored with the cochain complex, the cohomology complex for the given complex of vector spaces. And if F is a constructible sheaf of locally finitely presentable derived Tartin stacks, so algebraic, then for any local section, you have a relative tangent complex, which is a complex of vector spaces on the base. It's a constructible complex on the base, and then if you have a relative form in one of these diagrams, it defines a map from the P to H power of the tangent complex to E, as you would expect. And if you look at what this does on cohomology, on global sections, that's the value of the form at the point. So that's good. That allows you to talk about non-degeneracy. So if you have a stratified space with equidimensional strata, so I'm gonna assume equidimensional strata so that I don't need to say, make qualifying statements all the time. And a constructible sheaf of locally finitely presentable derived Tartin stacks. And you take your coefficients to be in the dualizing complex shifted by n.
I'm sorry, what's equidimensional? I mean, this is topological space, right?
No, remember, it was a good stratification. So a good stratification was locally conical. So you can talk about dimension of the strata. They're cones over affine spaces.
I mean, is it like complex space? or real or what? No.
It's real. No, it's real, but the strata are really essentially Euclidean spaces. Something
It's like in the Macpherson formula, right? Just
yeah.
okay.
It's slightly more general than that, but yeah, I mean, you can certainly talk about dimension.
Okay.
And the dimension of the stratum will be important. I mean, you'll see in a moment.
But it can be real. It doesn't have to be complex, right?
Doesn't have to be complex. And in fact, you'll see. I'll do examples in a moment. I mean,
Like S1.
All the examples are not going to be complex. Yeah. In particular, it's not going to be. I mean, Whitney stratifications will be good, but it's not necessarily going to be a Whitney stratification of a complex space. So yeah, so I have a constructible sheaf of derived stacks, which are all algebraic, and I have a coefficient complex, which for me is going to be just the dualizing complex shifted by some integer. Just the usual Verdier dualizing complex on the stratified space. And now you can define the relative closed p-forms to be and-shifted to be the closed p-forms on F with values in the dualizing complex shifted by n. And you can define the space of those, which is just as before, the cohomology or the topological realization of the dot count. And relative n-shifted 2 form is, so this should be 2. It's not p, it's 2. It's symplectic if for every open and every section over that open, the corresponding contraction with it. So you pull back the tangent complex by the section, so that gives you a complex, constructible complex of vector spaces on the open, on the base, and the form gives you a map to the cotangent, pullback of the cotangent complex shifted by the dualizing complex, tensored by the dualizing complex shifted by n, and you want this to be a quasi-isomorphism. That's the non-degeneracy condition. So it's just saying that T and L are Verdier dual up to a shift. Now with this, you can actually characterize relative forms which are non-degenerate explicitly in terms of combinatorial data. So if you have a sheaf of algebraic nice Artin stacks, locally finitely presentable, constructible sheaf, and you have a relative closed and shifted 2 form, then for every stratum, it induces an absolute shifted closed 2 form on the nearby cycles of the sheaf on the stratum. So the nearby cycles on the sheaf of stacks is just an algebraic stack on the stratum. And you get an actual symplectic form on that guy, respected by the action of the fundamental groupoid, which is shifted, and it's shifted by n plus n is the original shift plus 1 plus the dimension of the stratum. And you also get an isotropic structure on the co-specialization map. So there is a co-specialization map from the local system of stacks on the stratum to the nearby cycles on the stratum. And the nearby cycles are symplectic. Well, it's a shifted closed 2 form, the thing that corresponds to any closed 2 form. And you get an isotropic structure for that shifted closed 2 form. So that just comes out from the combinatorics. And then the theorem is that the relative form is symplectic if and only if the form on the nearby cycles for each stratum is symplectic, and the co-specialization map is Lagrangian for each stratum. So it's something that you can combinatorially check stratum by stratum. The data of the form really disassembles into these guys, and checking non-degeneracy is really checking non-degeneracy stratum by stratum, which turns out to be very useful. I mean, that's what allows you to do computations. Okay. And now here is the main tool for constructing forms. It's the push-forward theorem. So suppose that we have a stratified map of nicely stratified spaces, and you have a sheaf of stacks on the source and a sheaf of complexes of vector spaces on the source, then you can push forward the sheaf of stacks, and you can push forward the complex of vector spaces to get a sheaf of stacks on the target and a sheaf of stacks on the of vector spaces on the target. And these are computed by right-can extensions between the functors of the corresponding pieces of the exit path categories. So it's all computable. Then you can push forward a relative form, and it gives you a form on the push forward sheaf of stacks with coefficients in the push forward complex. And if the coefficient complex happens to be the dualizing complex on the source, then you get something in the push forward of the dualizing complex, and then you have a trace map to the dualizing complex of the target. And the theorem is that if the map is proper and you start with something symplectic on the source, the trace of the push forward is going to be symplectic on the target. So it gives you like a machinery for producing many, many symplectic forms from known ones. And in fact, I'll do the examples now. In fact, what's really happening is that this is some fudged up version of quasi-Hamiltonian reduction. It's like a system of quasi-Hamiltonian reductions done iteratively that are packaged by these sheaves of stacks or diagrams of stacks or diagrams of symplectic forms. Okay, so here is this comment that I made, which is that most of the standard constructions of symplectic structures actually arise as special cases of this push-forward theorem. So let me go over the examples, the standard examples. So if you have a topological space and you think about it as a stratified space with a single stratum.
So it's effectively a manifold then.
It's going to be a manifold in a moment, yeah. It's going to be actually an oriented manifold.
No, just nice stratification seems to imply that if there is only one stratum, it has to be a manifold.
Right. I mean, the goodness will say that it's an oriented manifold. Now, if you have a derived Artin stack, which is nice, smooth, locally defined presentation, and you look at the constant sheaf with fiber that stack on that manifold, then you can ask what is the data of a relative symplectic form for that constant sheaf? Well, if you have an actual symplectic form on the given stack F, the fiber of our constant sheaf, it does give you a relative close to form, which has values in the constant sheaf shifted by n. And when X is an oriented manifold of pure dimension D, then the dualizing sheaf is the constant sheaf shifted by D. So you can view this form, this global form on the fiber as a relative form with values in the dualizing sheaf shifted by n minus D. And then omega is non-degenerate as an n-shifted absolute form on F if and only if the viewing omega as a relative form, it's non-degenerate as a relative form n minus D shifted on F. And what the push forward theorem tells you is it tells you that so taking the push forward is just taking the global section of that constant sheaf. So this is just the mapping stack, all the maps from X to F. And it tells you that the trace of the global sections of omega is an n minus D shifted symplectic structure on that mapping stack. So that's the algebraic version of the AKSZ formalism and the mapping stack theorem from our paper with Bertrand and Michel and Gabriele. So it's just a special case of this push forward theorem, but a very easy special case. You also get Lagrangian, the notion of a Lagrangian as a special case. So if you take your topological space to be the half open interval, 0, 1, closed at 1, with strata, with two strata, you know, one open stratum, which is the open interval, and one closed stratum, which is the point 1. Then these are labeled by a 2-point set, the inner stratum and the closed stratum, with one less than inner. And then a sheaf a constructible sheaf of stacks on this guy is just two stacks, F1 and F inner, together with the co-specialization map. From the closed stratum, the value of the sheaf on the closed stratum to the value of the sheaf on the open stratum. The dualizing complex in this case is just the extension by 0 of the constant sheaf shifted by 1 from the inner stratum, the open stratum. And a relative n-shifted symplectic structure on F is an n+1 shifted symplectic structure on the guy on the inner stratum and an n-shifted Lagrangian structure on the co-specialization map. So it is just what a Lagrangian is. So a symplectic structure on this sheaf, on this constructible sheaf on this stratified space is just a Lagrangian on the fiber of that sheaf on the open stratum. And you can do that for two Lagrangians. So if you take the closed interval with 3 strata now, the open interval and the 2 endpoints, then a constructible sheaf of stacks on that, it's going to be 3 stacks, 1 for the open stratum and 2 for the closed stratum, with 2 co-specialization maps from the closed stratum to the open stratum. The dualizing sheaf is still the extension by 0 from the inner stratum of the constant sheaf shifted by 1. And so a relative symplectic structure on this sheaf of stacks is an n+1 shifted symplectic structure on the guy on the inner stratum and n-shifted Lagrangian structures for the 2 co-specialization maps. And the push-forward theorem tells you that the trace of the global sections of that guy is an n-shifted symplectic form on the global sections of the stack, but the global sections of the stack are the intersection of the 2 Lagrangians inside the inner guy, the derived intersection of the 2 Lagrangians. So this reconstructs this other theorem that we proved, that the derived intersection of 2 Lagrangians in an n+1 shifted stack is an n-shifted symplectic stack. So it's again a special case of this push-forward theorem. Hamiltonian reduction is a special case of the push-forward theorem. So if you take the stratified space to be the closed interval with the same strata as before, 1 open and 2 closed, and you take a linear algebraic group G and a cojoint orbit, O, and you have a symplectic manifold, algebraic symplectic manifold equipped with a Hamiltonian G action. So it has an equivariant moment map. Then this gives you a sheaf of derived, constructible sheaf of derived stacks on the interval. So on the open stratum, it is just the cojoint quotient. It's just the stack quotient of the dual of the Lie algebra by G. But if you stare at this for a moment, you realize this is the cotangent bundle of BG shifted by 1. So it's a shifted cotangent bundle. So this thing always has an intrinsic symplectic form, 1 shifted symplectic form. And then at the closed strata, you put the cojoint orbit modulo G as a stack and M modulo G as a stack. So the inclusion of the cojoint orbit in the dual of the Lie algebra gives you a map of stacks, which is Lagrangian. So that's actually the Lagrangian structure is the constant Kirov-Surreau form on the cojoint orbit. And the moment map gives you a map from M mod G to the open guy, and that's the other co-specialization map, and that's also Lagrangian. So you have this 1 shifted symplectic struct G dual modulo G, and you have 2 Lagrangians in it. And that's the constructible sheaf that you construct. That was the notion. And the global sections is the Hamiltonian reduction. So the global sections is the derived preimage of the orbit modulo G. So it's a derived stack, but as a derived stack, it's actually locally finite presentation. So it's now smooth everywhere. You don't have any conditions on stabilizers or properness or anything like that. And the trace of the global sections of the form is a 0 shifted symplectic form in this case on this guy by the push-forward theorem, which of course on the smooth locus is the Marsden-Weinstein form. But this now makes sense everywhere.
So this seems to say that Hamiltonian reduction is a special case of Lagrangian intersection.
First it says that Hamiltonian reduction is a special case of Lagrangian intersection, and then, you know, Because Lagrangian intersection was a special case of push forward, then it's a special case. And quasi-Hamiltonian reduction is also Lagrangian intersection, but it's also push forward. So you can write it as Lagrangian intersection, so you can write it as some constructible sheaf on the interval, but it's more natural to actually write it as a constructible sheaf on the two-sphere. So take the two-sphere to be our space with three strata again, the open stratum, which is the cylinder, which is the complement of the north and south pole, and the two poles. And fix a complex, now reductive group. Now the group has to be reductive. You know, in the previous case, there was no requirement about reductivity because the basic symplectic form was the symplectic form on the shifted cotangent bundle of BG, which always exists. For the quasi-Hamiltonian reduction, you need the group to be reductive. And you fix a conjugacy class and an algebraic symplectic manifold with a group valued moment map. Now you get a constructible sheaf on the two spheres. So at the two poles, you get the conjugacy class modulo G and modulo G, and on the cylinder, you get just BG. And BG is symplectic because G is reductive. So the choice of a Killing form gives you a two-shifted symplectic form on BG. And the map from C mod G to G mod G and from the moment map from M mod G to G mod G, these are Lagrangian. So these co-specialization maps give you a relative symplectic structure on this constructible sheaf of stacks. The dualizing sheaf is still the extension by 0 from the open stratum of the constant sheaf, now shifted by 2 because the dimension is 2. And the standard two-shifted symplectic form on BG extends to a natural relative zero-shifted symplectic form on that sheaf, constructible sheaf of stacks, whose trace of a push forward is exactly the zero-shifted symplectic form on the derived fiber of the moment map over that conjugacy class modulo G. So that's the Alexeyev, Malkin, Meineken quasi-Hamiltonian reduction theorem, again at all points with no qualifications.
So do I understand correctly that you need to use the sphere because you want to have S1 and topologically in the generic fiber, which gives you the conjugacy classes when you.
Yeah, I mean you could actually push forward in two steps, right? You could start with the sphere. We are pushing forward from the sphere to the point, but you could push forward from the sphere to the interval.
And that gives you
that gives you a constructible sheaf on the interval where it is actually a Lagrangian intersection. So there, at the two endpoints, you still have C mod G and M mod G, but on the open stratum, you get the conjugacy classes.
The inertia group, whatever they call it. Yeah.
Yeah. So you could do it that way, but it's more natural to do it with the sphere. Okay, so you see that this, as I said, this push forward theorem is just packaging, you know, combinatorially many Hamiltonian reductions and or quasi-Hamiltonian reductions and other constructions of symplectic structures. Okay, well, I'm 1.5 hours into it. So the next story is to tell you how do you do the symplectic structures or the Poisson structures on the Stokes data. And that's gonna take probably at least 10-15 minutes for the curves. And I don't think I'm gonna do the higher dimensions because it's gonna take forever.
You can do that's right. I mean, it's on the paper. But you can do the higher dimensions. I mean, it's on the paper, right?
It's yeah. I mean, it is in the slides. You can see it, but I'm not going to go over it because you'll see. I mean, even for the curves, it's going to take some time. But
sure, I just want to
like 10-15 more minutes or
absolutely
tired. Okay. So the idea. So we need to take this moduli of Stokes data, the derived moduli stacks of Stokes data, and construct a Poisson or symplectic structure on it. And we're going to do it by actually describing that stack in terms of a classifying object. So the same way, like the stack of G-local systems on a space is maps from that space to BG, we want to have the stack of Stokes field of local systems to be maps to something. And it's not going to be maps to anything. It's going to be sections in a constructible sheaf of stacks. And that's why we needed these relative symplectic structures in order to say that on the sections of a constructible sheaf of stacks, we actually get a Poisson structure or something. So here is the setup. Take a smooth surface X, which underlies a quasi-projective curve. We're going to stratify it by two types of strata, two types of open strata, inner open stratum and an outer open stratum. And the inner open stratum will be connected, the outer open stratum will not be connected. And then there will be one-dimensional strata, which will be arcs, will be labeled by E in E. And there will be endpoints of the one-dimensional strata, zero-dimensional strata, which will be vertices XB. And the stratification should satisfy the following conditions. Two arcs meet at each point. Each arc separates the inner and the outer open strata, and the outer open stratum retracts on the boundary of our surface. So this is the picture. So the whole thing, yellow and blue, is the surface. The inner open stratum is the blue part. The outer open stratum are these yellow cylinders. So it's one little cylinder near each boundary component. And the outer open stratum and the inner open stratum are separated at each boundary component by a circle. And now each of those circles is broken by Stokes rays into arcs. So it's broken by points into arcs. So that's the way that stratification looks like. And now I'm going to talk about a special class of constructible sheaves on these guys, which I'm calling the Lin-Milgrange-Stokes sheaves. So on an open stratum, so this is the condition that the sheaf should satisfy. On an open stratum, it's going to be isomorphic to the classifying stack. It's going to be locally constant sheaf with fibers BG for some reductive group G. And it's going to be this of the same type. It's going to be a locally constant sheaf of BGs on the inner stratums or on the outer stratum. And the groups will be different on different strata in general. And in particular on different connected component of strata will be different. But the only thing I'm requiring is that they're reductive, and it's BG for those groups, and it's locally constant on each open stratum. Now, on one-dimensional strata, the condition is that, so for each one-dimensional stratum, for each arc, the arc separates an inner and an outer stratum. So we have specializations of strata. The arc is in the closure of some of the inner stratum and some outer stratum. And this induces co-specializations of the values of the sheaf on the strata. So from the value of the sheaf on the arc to the value of the sheaf on the inner stratum to the value of the sheaf on the outer stratum. But remember, the value of the sheaf on the inner or the outer stratum was the classifying stack of a reductive group. And so the condition is that these co-specialization maps are just the maps to a BG on the inner stratum and a BL on the outer stratum from a BP, where G is a reductive group, P is a parabolic, and L is the Levy quotient of that parabolic.
And is the parabolic the same for all the arcs?
No, the parabolic depends on the arc. So the only condition is that on each arc we have its own parabolic, which is a parabolic in the given G, because on the inner stratum there is only one group. Mm-hmm. And then on the outer stratum for all the arcs for that stratum, the Levy for all those parabolics is going to be the same, but the parabolics are going to be different.
Okay, thank you.
Yeah. And so what happens when two arcs meet at a point? So you have, two arcs, XU1 and XE2 meeting at a point, and then the open strata have these arcs and this point in their closures. And you have co-specialization maps for the stacks going from the point to the arcs and to the open strata. And this should be, so, you know, one of the arcs has one parabolic that maps to BG and to BL. The other one has a different parabolic that maps to the same BG and the same BL. And on the point, you have the B of the intersection of the two parabolics. So this is just a group theoretic version of what we had for these Deligne labeling sheaves, where we had filtrations given by total orders on the arcs. And then at the point, we had the minimum of the two orders. So this is just a group theoretic incarnation of that thing.
But is there some kind of transversality condition for the two parabolics? Like, could they be the same, for example?
Well, yeah, they can be the same, but then, yeah, I mean, here it will be just the B of the parabolic.
Because you had a condition that the filtrations were opposite, yeah, in the classical situation, in the beginning of our talk. And here there is no similar requirement.
Yeah, I mean, this is more general now. I mean, you know, it's not a GLN situation.
Okay.
I mean, these Deligne-Lagrange Stokes sheaves. Of course, you know, the ones that are going to come from irregular types will have that property that these parabolics will be actually different.
Let me rephrase it. So the intersection is just the intersection of the derived intersection.
No, this is just the intersection, the intersection of the groups.
Okay.
This is the subgroup, which is the intersection of the two parabolics. Yeah, these are stacks. There is nothing derived in them. I mean, of course, the mapping stacks will be derived, but the coefficient stacks are just stacks. And what I just want to say is that, you know, you can fake this, you know, you can introduce extra zero-dimensional strata and put here the parabolic. It's just, you don't have any Stokes phenomenon there, so nothing really happens there.
I'm talking about geometry, so the diagram is not Cartesian. I mean, there are some squares there, but they don't have to.
No, the diagram is not Cartesian at all, no. It's just saying that the diagram has to be isomorphic to that diagram. It's just a condition on the diagram. Yeah. It's not Cartesian at all. Yeah, so here is the picture. We have BG in the interior. We have B of a levy on each cylinder. We have B of a parabolic on each arc, and we have B of an intersection of two parabolics on each point. And as I said, on the open strata,
excuse me,
yeah.
These parabolics, do they contain some fixed Borel subgroup or not?
No, they're just parabolics. But the only condition of the parabolics is that all the parabolics you see for the arcs here on this circle have the same levy quotient.
I mean, what do you mean by the same levy? You mean, okay, I think I know what you mean.
And one thing I need to point out is that so even if my sheaf is constant on the interior, these guys here on the cylinders may be only locally constant. So the levies may have monodromy on the circle. But they're the same levy subgroup of the conjugation. Okay, so here is the theorem. If you have one of these guys, one of these Deligne-Lagrange Stokes sheaves, then if you look at closed two forms with values in the dualizing sheaf on the surface, and restrict those to the open stratum, to the inner stratum, to the blue guy, then if you take a closed two form on the inner stratum, which happens to be non-degenerate on the inner stratum, so first of all, this restriction is a homotopy equivalence. So any form on the inner stratum can be extended to a relative form on the whole sheaf. And the non-degeneracy is just non-degeneracy on the inner stratum. If the form is non-degenerate on the inner stratum, then its extension to a relative form is a relative non-degenerate form. And so if, for instance, you know, if on the inner stratum you just have BG constant, then any killing form will be a symplectic form, and you'll get a relative symplectic form onto the whole Deligne-Lagrange Stokes sheaf. In general, you need to take a form if BG wasn't constant, if it was locally constant. you need to take a killing form, which is monodromy invariant.
May
or may not
sorry,
exist.
sorry, Toine, about the previous slide. So when you say they have the same parabolic, you mean some universal, the same Levy?
The same Levy quotient, yeah.
I mean, there is some universal Levy subgroup. So you mean this one, right?
Yeah,
somehow identify them.
Yeah. It means that there is a Levy subgroup sitting inside G that sits in both of them. And when you project to the Levy quotient, it's an isomorphism.
Really sits in both of them?
Yeah. It really sits in both of them. And when you project to the Levy quotient, it's an isomorphism.
Okay.
Yeah, so what I was saying is that, this guy on the inner stratum may or may not exist. I mean, if it's a constant, if it exists, if it's not constant, it has to be monodromy invariant and may or may not exist. But when it exists, it extends automatically to the relative guy and uniquely, and it's non-degenerate. And
you required contractibility, right? You required the outer thing to be contractible.
Say it again?
You required the
Yeah, say what you're saying here.
You require the outer thing to be contractible to the boundary, and this is exactly
to the boundary. Yeah. But this is about the inner thing, not the outer thing. Yeah, so this thing, I maybe should make this comment here, is that it's a pattern, it also happens in higher dimension. So what we're saying is that we have this sheaf of derived stacks, constructible sheaf of derived stacks on some space, and we're trying to construct a symplectic form, and it has a restriction on an open, and there is a symplectic form on that restriction on the open because it's constant there. It's a big dense open stratum, and what we're saying is that always extends to a relative guy, and non-degeneracy on the open is the same, extends uniquely, and the non-degeneracy on the open implies non-degeneracy. It's equivalent to non-degeneracy on the relative guy. And in each of the examples that we worked out, we actually proved it by hand. But it seems to be some perverse statement. So, these constructible sheaves of stacks must be perverse in some sense. They must be some kind of perverse Schobers if you write them in a correct way. And what this is saying is that there is a middle perversity extension from the open stratum, which is unique. And it gives you the sheaf. And so if you have a form on the open stratum and you extend it by a middle perversity, you get actually the whole thing. But we don't have a general statement like that. We, in the examples for the Stokes data, we actually did it by hand. We checked that the choices are contractible, and then the whole thing extends, and non-degeneracy is the same.
But in higher dimension, do we only still have X in and X out, or is it more complicated?
It's more complicated. Let me finish with dimension 1 and maybe.
Yeah.
Huh? Yeah.
I'm just saying, sure. Go ahead.
So this is saying that you need something locally constant. Okay, so here is what you do. Take a smooth projective curve, take these irregular types at the punctures. Now, what you really get is you get one of these Deligne-Malgrange, the irregular types give you for G local systems. So these are irregular types for G local systems. So these are Laurentals with values in the Lie algebra. And they give you the Deligne-Malgrange stock sheaf of derived stacks on the open guy, which classifies Stokes data of irregular type I. And in fact, what you get is that the Stokes filtered local systems filtered by the irregular type I are sections on the surface with boundaries that you get by taking this Deligne-Malgrange stock sheaf and restricting it to that surface with boundaries. So this surface with boundaries is just the real-oriented blow-up of X at the points. So just introduce a boundary circle near each boundary component. And so it's really this constructible sheaf that's defined by the irregular type, and you have global sections in it. And so now the push forward theorem kicks in. so the sheaf that you get, it satisfies the 0, 1, 2 properties that I specified. The local systems I'm looking at, they are untwisted. They're G-local systems, not local systems for some locally constant sheaf group scheme with fiber G. So if you choose a killing form, then that gives you a symplectic form on the open stratum, and that extends uniquely. And so this Deligne-Malgrange-Stokes sheaf that we get actually does have a symplectic structure. And in general, if you have any Deligne-Malgrange-Stokes sheaf of stacks equipped with a kx valued relative symplectic form, you can take your surface and map it to the half open interval. And this is a proper stratified map. It contracts the complement of the outer stratum to 1 and projects each cylinder component. So it basically contracts the closure of the inner stratum to 1, and it projects each cylinder component of the outer stratum to the open interval 0, 1, to that neck. And it's a proper stratified map, and if you take the trace of the push forward, you get a K01 valued symplectic structure on the push forward. This gives you actually a one-shifted symplectic structure on the sections over the outer stratum. And the trace defines a zero-shifted Lagrangian structure from the closure of the inner stratum to the outer stratum, sections over the closure of the inner stratum to the outer stratum. And if F was the Deligne-Malgrange-Stokes sheaf corresponding to the irregular type, then the thing that corresponds to the closure of the inner stratum is just the local systems, Stokes filtered local systems, whereas the thing that corresponds to the outer stratum are local systems on the boundary circles for a structure group which is actually locally constant. It's a local system of Levy subgroups on each cylinder. That's because, you know, so when I didn't quite explain how you get these Deligne-Malgrange-Stokes sheaves, but you know, remember there was this Deligne guy that labeled the steps in the filtration, and I said that as a sheaf of sets is locally constant, but it doesn't have to be constant. So it can consist of a bunch of circles that wrap on the base circle. And that wrapping actually twists these families of levies and gives you a local system of levies. So you get the natural map from the inner to the outer, which is Lagrangian. This map is the formal monodromy. So it takes a Stokes filtered local system and passes to the associated gradient with respect to the Stokes filtration and takes the monodromy on that. So that's this map. And or you know, another way to say it is you take the Stokes filtered local system that has a low in the de Rham setting, you take meromorphic connection that has an irregular singularity. By a formal gauge transformation, you can make the singularity regular, and then you can take the monodromy of that regular singularity. So that's the same map. That map is Lagrangian, and so the intersection, which is the modular space of Stokes filtered local systems with fixed conjugacy classes of formal monodromy, is going to be symplectic. So the Lagrangian map gives you a symplectic groupoid, so that gives you a Poisson structure, and if you intersect it with fixing the conjugacy class of the formal monodromy, which are a Lagrangian in this boundary guy, then you get something symplectic, and these are the symplectic leaves. So this gives you the full picture for surfaces. And okay, so I'm going to stop there. This you know, the rest of the story is about hard dimensions, but yeah, questions.
Yeah, let's thank the speaker, I think. Indeed, questions.
I have a question. You promised the classification of the orbits, right? Of symplectic leaves, sorry.
Yeah, I did it. That's, you fix a formal monodromy. So remember, the symplectic structure is on this guy. The Poisson structure is on this guy. There is a Lagrangian map that describes that Poisson structure. So it's the map that sends the Stokes filtered local systems to Levy local systems on the boundary circles, which is the formal monodromy map. So that's a Lagrangian map in this symplectic guy, because these are just local systems with reductive structure group on the circle. So these were symplectic. These are one-shifted symplectic. And so this is a Lagrangian in there. And that Lagrangian structure is really the Poisson structure on the source. And now if you fix a conjugacy class of the formal monodromy, so if you fix the conjugacy class of the monodromy of these Levy local systems on the circle, that's another Lagrangian. That's this guy that I wrote here. And so if you take the Lagrangian intersection, that's the moduli space, subspace of Stokes filtered local systems with fixed conjugacy classes of formal monodromies. And that is the symplectic leaf. So if you fix the conjugacy classes of the formal monodromies, if you vary them, that gives you all the symplectic leaves.
Okay.
I mean, it doesn't give you all the symplectic leaves, it gives you a natural family of symplectic leaves. Yeah. You know, with these derived stacks, you have to be careful because remember, symplectic guys that map to a Poisson guy, the same way Lagrangian guys that map to a symplectic guy were just maps, they weren't subs. So, so you can have many symplectic leaves coming from different sources. So there are other symplectic leaves you can construct, for example. For instance, if you take any handle body.
Any what?
Any handle body,
Okay.
any three-manifold that bounds your surface. And you take a knot in that three-manifold that cuts out the points, a link in that three-manifold that cuts out the points, the Stokes points at the boundary. That will give you another symplectic leaf. It will give you another Lagrangian in this guy on the boundary, and you can intersect with it, and it will give you another symplectic leaf, which is not one of these. So there are many different symplectic leaves you can imagine, but this is at least a natural family of symplectic leaves.
I see.
And where are the slides available?
Yeah.
Where can I find them?
I can.
No, the seminar webpage.
Yeah, I'm gonna send them to somebody, and they can put them in the seminar webpage.
If you want to consider regular singularities, then this corresponds to what? To the situation when you don't have points on.
Yeah, regular singularities. It's just saying that no, you don't have any stratification. There is only one stratum, one open stratum. So it's just mapping stack from the open surface to the BG, and that is also symplectic. Sorry, Poisson. So mapping to conjugacy classes of monodromy now at the boundary gives you a Lagrangian structure, and fixing the conjugacy class of the formal monodromy gives you symplectic leaf.
I mean, it's not like they have no stratum. They have the open stratum and then the boundary components, right?
Well, but the boundary components we put in by hand by just taking, you know, a circle near the boundary. I mean, the way I set it up, you know, my surface was with necks, you know, it was open. It didn't have boundary. But you could say, yeah, I mean, let's have boundary.
Okay. No, just I mean, from the formalism, if you want to map to the interval, you need something to.
Yeah, I need to actually introduce a boundary. So I need to take the blow up at the points to introduce a circle at the boundary, and then it's still gonna map to the interval.
And can I ask a general question? I mean, it's about higher dimension, but still, I mean, how important? I mean, why do you need X to be essentially a stratified manifold? This is only for Verdier duality type of things, right?
Yeah, I mean, as I said, you know, the push forward theorem, the notion of a form, the notion of a non-degenerate form, it works for families of stacks on any locally compact Hausdorff space.
Right, locally compact should be.
But everything works. The problem is that you want to compute, you know, if you want to prove that symplectic form exists, you want to compute something. And when you deal with this covariant Verdier duality on locally compact Hausdorff spaces, it's very hard to compute things. So that's where the stratifications and the combinatorial picture comes in.
Things like, I don't know, totally disconnected things, I don't know, like a padding group, right? Okay.
Yeah.
I mean, did people consider that? I mean, still locally compact.
Well, I don't know who considered it. I mean, you know, this is fairly new. I mean, we haven't yet actually written the paper yet, right? I mean,
okay.
I mean, you know, people have considered stuff like that in the tame case arithmetic situation. So there are these papers by Venkatesh and Manolescu, maybe. I'm gonna mess up the names, but Venkatesh is one of the main people, where they look at actually unramified local systems on curves over number fields.
Mm-hmm.
And there the derived structure is important because the stack is actually singular, it's non-reduced. It could be non-reduced. And you need the derived structure to actually make it with a perfect tangent complex. And you can actually rewrite that in terms of the push forward theorem on something that's totally disconnected, but we haven't quite done it. You know, we just looked at it briefly.
Okay. More questions?
Everybody's exhausted.
Just a general remark, because people keep asking. I mean, all the materials from the seminar are available on the seminar webpage, which you can find easily. It's on mat-net.ru, or you can just go to the Steklov Institute. There's a link. I mean, there's a lag, right? So, I mean, typically a video would appear like 2 or 3 days after the talk, but it will appear there.